Hello students, today is day 1 of lesson 6 where we're going to learn about ecosystems and climate for environmental science. Your teacher is going to start your class for this day with this bell ringer, and it is a quote to reflect on. This is: "A nation that destroys its soils destroys itself. Forests are the lungs of our land, purifying the air and giving fresh strength to our people." Quoted by Franklin D. Roosevelt. So what do you think this quote means? Make sure you answer the question and submit it to your teacher as required or requested by them. So for lesson 6.1, we're going to investigate what factors influence climate. So throughout this lesson, you're going to learn the differences between weather and climate, the relations of the ocean and the circulation to Earth's climate zones, the greenhouse gases that are in the atmosphere and how those gases affect the Earth's atmosphere. And you're going to learn about rain shadow effect and explain how it affects climate. Some key terms we'll cover are listed here. As you go throughout this unit, you will see those key terms are going to be highlighted. And it is important in science to make sure you understand the language of science. So a lot of science, in order to be successful, you really truly have to know the vocabulary. So spend some time learning these terms when you have an opportunity to practice. Your teacher could direct you to a Quizlet that may be available or may have printed flashcards for you. So when we look at climate, it differs from what we consider weather. So it's a very common misconception in everyday language, the misuse of the terms climate and weather. So when we look at climate, the biodiversity of a region is basically defined by climate. Climate is different from weather. Weather is a set of physical conditions of the lower atmosphere. So it includes like temperature, precipitation, humidity, wind speed, cloud cover, and other factors that are given in a period of over hours or maybe a few days, or up to 10 to 14 days, depending. And the further out you get when you look at weather, you're going to see that the accuracy of predicting weather becomes poorer the further out that we go in terms of time. And so weather fluctuates generally daily and seasonally. So climate, on the other hand, involves a pattern of the atmospheric conditions in an area over a period ranging from 3 decades to thousands of years. So it's the typical or average weather that is seen in that location. So it's going to be affected by solar energy, the Earth's rotation, global patterns of air and water movement of gases in the atmosphere, and the Earth's surface features as well. So it occurs more slowly than and so the change of climate would occur slowly compared to weather changes. So when we look at climate change, climate can be caused by natural events. It can be caused by changes in the Earth's orbit. It can be caused by the amount of energy that is reaching the sun's surface, volcanic eruptions, and even changes in the ocean. It could also be caused by human activities, as humans are changing the atmospheric gases and the composition of and proportions of those gases. And the average weather conditions over the past 30 years can be a signal as to how the climate may be changing. So there's a video linked here below that we'll pause and take a moment to watch.
We hear it so much that it feels like a buzzword, but it is far from it. Climate change is a real and serious issue. But isn't the climate always changing? What exactly is climate change? Why should we care? Well, the Earth's climate has changed throughout history. Most of these slight changes are caused by small variations in the Earth's orbit. But climate change as we know it today is characterized by an abrupt increase in the Earth's temperature. It is estimated to have gotten 1.2 to 1.4 degrees Fahrenheit warmer in just the last century. 10 out of the last 13 years were the warmest on record. 97% of climate scientists agree that this new tendency is not caused by the variations of the Earth's orbit, but rather very likely caused by human activities. That means you and me And since the Industrial Revolution, we have come a long way. Humans built airplanes, faster cars, developed remarkable technology, and learned how the natural resources around us can be used for our benefit. Although this has led to many wonderful inventions and advancements, like the device you're using to watch this video, or the ability to take a plane halfway around the world, it also means we've increased our consumption of natural resources and, in turn, released a lot of greenhouse gases into the atmosphere. Now, greenhouse gases occur naturally, but in excess can be dangerous to our planet. Modern human activities have increased the release of non-naturally occurring greenhouse gases because we have stepped up our demand for burning fossil fuels. The composition of greenhouse gases traps heat radiated from the sun. The more heat they trap, the warmer our planet gets. And as our planet gets warmer, we begin to feel the effects. One of climate change's biggest victims is our oceans. Oceans regulate the Earth's temperature and provide 50% of the Earth's oxygen. And climate change has increased the global temperature of the oceans by more than 0.3 degrees Fahrenheit since 1969. Although a warmer ocean might seem inviting to a beachgoer, it actually has devastating consequences for supporting life at sea. One of those consequences is ocean acidification, a direct effect of increased dissolved CO2. Since the late 18th century, ocean surface acidification has increased by 30%. A higher acid content means calcifying species, like oysters and clams and shallow water corals, are at risk, putting the entire ocean food web at risk. This is bad news for the 1 billion people relying on the ocean as its primary source of protein. Climate change has also caused the sea level to rise. Just in the last century, sea levels have risen 6.7 inches, but the rate in the last decade is nearly double. Sea levels have risen because as the ocean gets warmer, it swells. On top of that, glaciers and ice sheets are melting. Antarctica lost 36 cubic miles of ice between 2002 and 2005, and since 1994, each year on average, the Earth has lost 400 billion tons from its glaciers. That's like an ice cube 7.5 kilometers on a side, 4 miles on a side, melting and flowing into the sea. When all that ice melts, it fills up our oceans, and just like filling up a bathtub, the shores can't hold all that water, and coastal regions get flooded. Troubling signs of climate change are increased extreme weather events. Natural disasters like floods, tornadoes, and deadly heat waves are more obvious to humans because of their immediate impact and their sharing of the images in the media. Climate change, as we know it today, is change in our Earth's overall temperature with massive and permanent ramifications. Although its consequences can be planet-threatening, scientists still believe there are things we can do on a personal level to help. Recycle and reuse things. Walk or use public transportation to get to work. Turn off your electronics when you're not using them. Eat less meat. While you're at it, eat more locally grown vegetables and foods. And last but not least, spread your knowledge and concerns about climate change with others.
So after watching that video, we have a little bit better of an understanding of some of the impacts that climate change could actually have. So there are climate zones, and they tell a general idea of how the climate is in a particular place. So the climate near the poles, they tend to be cold, and the climates near the equator tend to be warm due to the amount of radiation they're receiving from the sun. So the ocean currents actually have a major effect on the climate as well. So other than just the location from the equator, it's also the ocean's currents. So they are mass movements of surface water driven by winds and landforms. So the temperatures are going to be affected because of the uneven heating by the sun due to the Earth's rotation on its axis and the physical properties of the actual oceans and land. So the more land there is, the more radiation is going to be absorbed by that land and re-radiated into the atmosphere. The more water there is in that region, the longer it's going to take to heat up, because that water has a high specific heat. It's one of the properties of water. So, and the air all surrounding there, the mountains, all of those things come into play to help determine how the temperatures are going to be impacting, or how the temperatures are going to behave on the planet. So there's a lot of different factors, which makes meteorology a tough field to be in when trying to predict things like the weather. So the uneven heating on Earth's surface is directly related to how the sun rays come in and strike the Earth. So it's going to lead to higher temperatures. So generally, if you're near the equator, you will experience higher temperatures and more direct radiation. The sun actually strikes at a lesser angle near the poles, leading to cooler temperatures. So the regions between those two areas have kind of a blend of warm and cool temperatures. So as you go away from the equator towards the poles, it generally gets cooler and cooler. So that intense input of radiation in tropical regions generally leads to increased evaporation of the moisture. So in that area, you can have greater precipitation in certain areas versus others because of that increased evaporation. So here's kind of a look. If we look at the sun, remember our Earth's axis is on a tilt, so that tilt actually leads to how we do not receive direct radiation year-round, so and also contributes to our seasons. So as the Earth rotates on its axis, the Earth's surface near the equator spins actually faster than the regions at the south and north. So this is generally what's referred to as the Coriolis effect, where air masses moving north and south appear to turn or deflect in relation to the land below them. And the Earth's rotation also helps lead to what's called prevailing winds, which there are named the trade winds, the westerly winds, and the easterly winds. So the next thing we're going to do is watch a video on the Coriolis effect to kind of explain how this all works.
What's going on here? Every time I throw the ball straight, it seems to bend to the side. No matter what I throw, no matter how straight I throw it, the ball seems to be curving. Maybe it has something to do with this. That whole time I was spinning, which is why it looks like I'm about to puke. That curve is created by the Coriolis effect. You may have heard that it makes water in the bathtub spiral down the drain a certain way, or that it determines the way a toilet flushes. That's actually wrong. Those are not caused by the Coriolis effect. But the Coriolis effect is what makes hurricanes spin, and it's the reason why Jupiter's Great Red Spot is spinning the way that it is. So what is the Coriolis effect? Well, it's what happens when objects moving in a straight line appear to curve because you are rotating. And it affects all kinds of things. It bends the paths of missiles and sniper shots. But how does it work, and how does it create hurricanes? Right now, it seems like the ball's curving, but let's take a look at what's really happening. My friends and I put together this little experiment using a sort of spinning seesaw. Here, the camera's standing still. It's just hanging from the ceiling. And watch what happens. From the moment the ball leaves my hand, it's just going straight. Let's watch that again, frame by frame. Keep your eye on the ball. You can see it travels in a perfectly straight line. But what if you're spinning with the seesaw? Look at what happens when you rotate the footage so the seesaw stays sideways and everything moves around it. Now let's follow the path of the ball again, but from this new perspective. The trajectory looks completely different. Now let's watch this one frame by frame. From this rotating perspective, it totally looks like the ball is curving. That's crazy because you already saw that exact same throw. Watch it again on the left. The ball is going straight. But on the right, when you're rotating with the seesaw, the ball really looks like it's curving. You might be thinking, why should I care? I don't spend a lot of time on a spinning seesaw or on a merry-go-round. But you kind of are on a merry-go-round. The Earth is constantly spinning. Have you ever seen someone in a movie making fine adjustments on their gun? Well, one effect they're correcting for is the Coriolis effect. The longest sniper shot, which was over 3,000 yards, would have had to correct for a 1-foot deviation due to the Coriolis effect. So how does the Coriolis effect create hurricanes? Hurricanes form when air rushes from all directions into a low pressure region. So imagine there's a low pressure region between the two of us. air is going to rush toward the center. Let's see what that looks like from space, from our camera that's hanging from the ceiling. It's not spinning, so the air, or in this case the balls, are clearly going in a straight line. But if you're rotating with the Earth, or with the seesaw, you'll see the air bend to the right. In the northern hemisphere, this creates hurricanes with counterclockwise spirals. In the southern hemisphere, it does the opposite. It creates hurricanes with clockwise spirals. This storm on Jupiter, which is actually bigger than the Earth itself, has been spinning for at least 200 years, largely due to the Coriolis effect. So when you're in a rotating frame, the Coriolis effect seems to exert a very real force on objects. But there is no force. What you observe is just a result of your perspective. And you might be wondering, if this is simply a product of your frame of reference, then could other forces like gravity or electromagnetism also just be products of your frame of reference, of where we live in the universe or in the multiverse? For more on that, check out our video, Do We Live in the Multiverse?
Okay, so with that video, hopefully you have a little bit better of an understanding of how the Coriolis effect actually works. And you can see here, as the Earth's rotation is, as the items on Earth, like for example, if we look at this hot air balloon right up here, located at number 2, if it was moving in the direction of south, you can see the actual direction of this balloon as the Earth's spinning. So the Coriolis effect is what is creating these spiral movements that we see in things like hurricanes. So with that, heat from the sun actually evaporates ocean water and transfers heat from the oceans to the atmosphere, especially near the equator where we have higher amounts of radiation, more energy, and the ability of that energy to create evaporation. So this creates giant cyclical Hadley cells that are able to move air, heat, and moisture vertically and place to place in the atmosphere. So those cells actually transfer energy by convection, and convection is a physical process which warms the where the warm, wet air actually rises into the atmosphere and then cools. And when it cools, it becomes less dense, or rather more dense, and falls back towards the Earth. And when it does, it generally is in the form of precipitation. So as it cools off, it condenses and results in precipitation. So that cool, dense air shrinks back to the surface, warms up, and then absorbs moisture as it flows across the Earth's surface, and it begins that cycle again. So the sun is driving these massive convection currents. So the Hadley cells are formed through what's called prevailing winds, or air circulation patterns, or configurations of continents and oceans based on the configurations of the continents. So it leads to irregular distribution of climates and resulting in grasslands, deserts, and forests based on how these large cells of air move. So the ocean currents are affected by the vertical movement of water. So denser water actually sinks while less dense water rises, and it creates a kind of a connected loop of this deep and shallow water. And those transfers of hot and cold water between the poles take about 1,000 years to circulate, but do play an important role in how the climate is behaving. So another thing that impacts climate is topography, and that's basically the shape of the Earth's surface. So clearly the Earth is not all flat. There are areas that have mountains, and some of those mountains are larger than others, but those features affect climate. So mountains actually interrupt the flow of some of those prevailing winds and the movement of storms. So areas of windward side experience precipitation, and areas on the leeward side are tending to be dry and warm. So as we go up in elevation on a mountain, it generally gets colder. So when air gets colder, it holds less moisture, and therefore precipitation occurs on the side of the mountain that the air mass is moving up. And then by the time it gets to the top, it's usually kind of exhausted or precipitated all of the rainwater or snow or whatever it may be. And on the other side, we have a drier, warmer area. A rain shadow, it results in a semi-arid or arid condition on a leeward side of a high mountain range. So those are the areas on the back side of the mountain, and that is an area that is just going to experience a low amount of rainwater because of the fact that most of the moisture was left on the other side of the mountain. So your exit ticket that your teacher may ask you to submit, so please make sure you take a moment to do that and have that prepared for them, is what is the Coriolis effect and what causes it? And that concludes our Day 1 presentation notes. I hope you found that helpful.